All right, welcome to 40 Minutes of Competence. This is the fuel heat value edition. And our question today is, what is the cost of heating a building with with a natural gas boiler, given that peak heat loss is 500,000 BTUs per hour, that there are 2,000 full load hours in a year, that the fuel heat value of natural gas is 1,000 BTUs per cubic feet, that the fuel cost is $11 per 1,000 cubic feet of natural gas, that the boiler efficiency is 90%. And I encourage you to utilize the formulas available to you on the exam. So if you go to my NCARB and you go to the practice exam or the demonstration exam on the right hand side, and you click accept a bunch of times and kind of go through the red tape. Then you are given the demonstration exam, and as I've pointed out before, you can click on references, and on the references you have acoustic, electrical, HVAC, plumbing, and structural tabs. And as such, you want to click on this one you'll want to click on the HVAC. And you see there are two formulas that are relevant to us. It's these two. Now, as an aside, you don't need those two formulas. If you understand if you can convert centimeters to miles, then you can surely convert these numbers into a certain number of dollars. It's actually pretty straightforward if you kind of follow the units. But we'll go ahead and go through it anyway. So what I just circled is this right here, that BTUs per year is equal to the peak heat loss times the full load hours per year, and that is given on the references formula sheet for HVAC. And that dollars per year is equal to BTUs per year times fuel cost divided by fuel heat value times efficiency. And so what we're doing is we're going to convert our peak heat loss and our full load hours per year into some amount of money it's going to take for us to heat our building. So that's what we're trying to figure out. We have a boiler, and the boiler, of course, heats up water, and that water gets sent around your building, and fan coil units and air handling units blow air across them, and radiators through radiant heat exchange and convective heat exchange heat the occupant and heat the air, respectively. And the question is, how much money are we going to spend to do that? And as you might imagine, if we're trying to figure out how much money that we have to spend to heat our building, we need to know certain things like how much heat does our building need, and what kind of fuel does it use, and how much does that fuel cost, and how much does a unit of that fuel provide us in terms of how many BTUs. That's kind of if there is a complex part in this one, and there's not really, but if there is one, it's that idea. It's the idea that we can get 1,000 BTUs for every cubic feet of natural gas. And you remember from the Amber book that a BTU is a British thermal unit. It's a unit of heat. And specifically, it's how much heat energy it takes to heat up 1 pound of water by 1 degree Fahrenheit. So this peak heat loss is 500,000 BTUs per hour. That means on the coldest day we have calculated for our building, we're losing 500,000 BTUs per hour, which is enough to take 1 pound of water and raise it in temperature by 500,000 degrees, or to take 500,000 pounds of water and raise all of that by 1 degree Fahrenheit. All right, so we'll take what we were given in the problem, and we'll put it up here in the corner for your reference, and we'll take what we found on the exam is given to us as part of the formulas, and we'll put it right there. And we'll pull out this one right here, and we'll bring it over here, and we'll start to figure it out. So BTUs per year, that's what we're trying to figure out, how much heat per year. And that's going to be equal to the peak heat loss times the full load hours per year. Now, as always, don't just look at that as an abstract set of formulas that you can plug in. You have got, if you're going to study for this stuff, man, it is way more fun and way more useful both for your career and for the types of problems that you're not going to see in your practice, the practice that you do during the study process. It's way more important that you understand it than that you memorize it. or even that you were able to plug it in. You just need to be able to understand it. And so what this is saying, it's saying, let's say this is how much our heat loss. And heat loss is kind of a complex idea. It's just the idea that there's heat leaving your building. So it's wintertime and your building is heated, and that heat is gonna go out the windows through conduction and convection. It's gonna go through the walls and the roof through conduction and so forth. And so looking at that heat loss over time, over the course of a year, maybe in January it's going to be quite high. There's a little warm spell, so when there's a warm spell it goes down, and then it's going to go like this, and it's going to probably be 0 over the winter months, or summer months rather. And then, you know, beginning maybe in late September, depending on where you live, it's going to start creeping up again. And so we have, we're kind of, in terms of how much fuel we need, which is really what we're trying to figure out here, how much we're going to spend on fuel, it's going to be akin or proportional to the area under this curve. Because if we have a longer winter, then that curve is going to kind of go here and there'll be more area under the curve. If we have a more severe winter that's not longer, it'll be up here like this, and we'll have more area under the curve. So in either case, here's a more severe winter. So in either case, it does a good job of kind of describing how much heat we're going to lose over the course of a year. Now, as you might imagine, it's hard to take that graph and put it into a single number, but we really can. We want to figure out how many BTUs we're losing per year through convection conduction generally. So one way to look at that is in terms of what's called full load hours, and that's just what it per year, and that's just what it sounds like. So it's the peak heat loss. So say the peak heat loss that we designed for is right here. And we can say, okay, we're using enough fuel to be equivalent to, say, this many months of running the thing full time. So all this area right in here, that would be that number of hours, this distance right here on the x-axis of time, that number of hours is our peak, our full load hours. So we can take the peak heat loss, multiply it by the full load hours, and we get an area that's equal to the area that was under the curve. So we're just taking one measure regime and swapping it for another. And we know that our peak heat loss is given as 500,000 BTUs per hour. And again, what does that mean? That means at the worst case scenario, that's how much our building is losing. So that's this number right here. It just came from here. And then now we need our full load hours per year. And so our full load hours per year is given as 2,000 full load hours per year. That's right here. So we're going to take 2,000 and we're going to multiply it by 500,000, and we're going to get 1 billion. And that's what we're going to get. We're going to get 1 billion BTUs per year. So that's how many BTUs we're going to burn that's how many BTUs we're going to lose in a year in our building. Now that also happens to be how many BTUs that our boiler needs to add back to the building to keep the whole thing in balance. So to keep the temperature steady inside while the building is losing heat, we're going to have to be dumping BTUs into the building at the approximately same rate as we're losing BTUs through the windows and the walls and the roof. And of course the slab a little bit and maybe some other places too, but generally that's what we're talking about. Heat loss through air infiltration and heat loss through conduction. So we have 1 billion BTUs, and we're going to take this number and we're going to put it over here on the left and kind of save it for later. So 1 billion BTUs per year, that's what we're losing. Now that brings us to our second formula that we're given, which is our dollars per year is equal to our BTUs per year times our fuel cost divided by our fuel heat value times our efficiency. Now, as always, don't just look at that and say, okay, got it. Just really kind of get it. Well, how much money do you spend per year on heating? Well, if we double our BTUs per year, if we double this to 2 billion, then you can imagine we would spend twice as much. So it makes sense that how much we spend per year is a function of how much heat we're losing, which is a function of how well insulated our building is, how airtight our building is, how much internal gains we get from heating, from lighting and equipment and from people, and of course our climate. It's going to behave much more differently in Missoula, Montana than it will in South Central Arkansas. So anyhow, it's how much heat we're losing per year. Okay, that makes sense. Times our fuel cost. Okay, how much does our fuel cost? In this case, natural gas. Well, if the price of fuel doubles, then our dollars per year would double. So that makes sense, our fuel cost. Divided by the fuel heat value. This is the only one that's really kind of a head scratcher a little bit, but not too bad. Our fuel cost is our fuel heat value is 1,000 BTUs per cubic feet of natural gas. So if you have a cubic foot of natural gas in volume, the question is how many BTUs could that theoretically provide if we had a perfectly efficient boiler? And the answer happens to be, for natural gas, about 1,000 BTUs per cubic feet. So every cubic feet of natural gas that we're taking out of the earth and pumping through pipelines and eventually bringing to your building is going to provide you, theoretically, if we could burn it really efficiently, with 1,000 BTUs. And that makes sense. If we got twice as many, if we got 2,000 BTUs per cubic feet, and we doubled this number in the denominator, well, then we're getting twice as much heat for every cubic feet, and you can imagine our dollars per year would go down by half. So if we double the fuel heat value, then we would actually have our expense in dollars per year. And NCARB does some kind of wacky units, dollars per year, and it's just a little weird. Times efficiency, because we're not taking that cubic foot of natural gas and burning it exactly, efficiently. Anytime we do combustion, we're going to have exhaust. And anytime we do exhaust, if you've been near an exhaust pipe, it's generally hot. So we're losing some of the heat from the natural gas up the pipe. Now, as an aside, some boilers are much more efficient than others. So in your practice, if you're in a cold climate or a mixed climate, and you have a big building that has a boiler, you should be inquiring to your mechanical engineer about what's called a condensing boiler. A condensing boiler is about 10% more efficient. It's more than 10% more efficient, but it'll burn this cubic foot of natural gas about 10% more efficiently. So generally, a non-condensing boiler, and a condensing boiler basically recaptures some of the water that's given off as part of the combustion process, and it condenses that water and it gets the heat of vaporization of that water. So there's a process in those kind of boilers that make them more efficient. And they're pretty much required or heavily subsidized in the advanced countries that are not us. There's often a subsidy for in America as well. But it's also meaningfully more efficient, because a regular non-condensing boiler maybe is 70 to 80% efficient, and a condensing boiler is more like 80 to 90%, or even up to 98% efficient. So in our case, we have a condensing boiler, but not a super efficient condensing boiler. But condensing boiler is a more efficient class of boiler, and our boiler efficiency is 90%, which is pretty good. So that means that for every cubic foot of natural gas, or for every BTU that we're going to burn, we're going to use 90% of that to heat up water that's going to go around the building and heat up air and heat up spaces. And we're going to lose about 10% of that's going to kind of go up the chimney. All right, so let's take these numbers and plug them in. So our dollars per year, we're just going to take this formula and bring it down. And we're replacing our BTUs per year with our billion number, 1 billion BTUs per year. And we figured that out before. That's how much heat loss we have in our building. So it's 1 billion BTUs per year. And then we're going to multiply that by our fuel cost. So our fuel cost is $11, but it's not $11. It's not $11 per cubic foot of natural gas. It actually happens to be $11 per 1,000 cubic feet of natural gas. So we'll have to do 11 divided by 1,000. Per foot of natural gas, it's actually something like, I guess, 1.1 cents maybe. We would move the decimal point 3 places over, so 1, 2, 3. Yeah, I don't know if that's 11 cents or let's figure it out since I brought it up. We have $11 per 1,000 cubic feet, and we'll bring that over 1, 2, 3. Then we have $0.011. Yeah, that works out to be like 1.1 cents per cubic foot of natural gas. But don't worry about all that. You can leave it as 11 per 1,000. Or in my case, I don't like having, when I'm explaining stuff to people, I think it gets a little confusing when there's a number in the denominator, but that whole number is in the numerator of a different, bigger fraction. So I'm going to get rid of that 1,000 and say, okay, it's 11 per 1,000 cubic feet of natural gas. So instead of this 1 billion number, I also don't like numbers that big, that's awfully big. I'm going to divide this number by 1,000 so I can get rid of that number. But you could leave it in if you wanted to. And so that billion BTUs per hour is now going to be 1 million, and it's no longer BTUs per hour. We have a different unit because we divided by 1,000. But we have a million now. We just have easier numbers to work with. All right. So our dollars per year is 1 million times 11 divided by the fuel heat value times the efficiency. And so what we need is we need to take that fuel heat value. The fuel heat value of natural gas is 1,000 BTUs per cubic feet. So that means for every cubic foot of of natural gas, we're going to get theoretically 1,000 BTUs out of that. And so that looks pretty good. And then we need our efficiency. So our efficiency is given as 90%. So we can take that number and bring it down, and we can say, okay, we're at 0.9. That's our efficiency. So then we can take 1 million times 11 divided by 1,000 times 0.9, and we wind up getting our dollars per year is $9,900. Now again, don't just look at that. What does that mean? Well, that means that's what we're paying per year for our heating. And for a big building, that seems kind of reasonable, $10,000 a year. You want to make sure if it said $300,000 a year, well, I guess it's possible for an uninsulated, very large building with very expensive fuel. And in terms of that expensive fuel, the fuel cost, here it's measured in $11 per 1,000 cubic feet, and that's pretty common. Per 1,000 cubic feet is kind of the number if we're dealing with natural gas. If we were heating with electricity, it would be per kilowatt hour. If we were heating with home heating oil, it would be per gallon. If we were heating with coal, like we do on campus here at Virginia Tech, it would be per ton of coal. So obviously, we have different types of fuels that you might see in your career or on the exam. But they're just going to be measured based on volume or based on how much electricity you've used, or based on tons or gallons of fuel, whatever. You get the idea. So that's our answer, $9,900 per year. That's what we're paying for heating. All right. Now, in terms of our question of the week, I pulled this came this week from the community, and I thought it was one worth tackling. This person said, hi, I would like to know the community's opinion on this matter. Is it best as an inexperienced recent graduate or as a seasoned architect several years after graduating? And the answer is yes. There is no bad time to take the AREs. People who are just out of school benefit because a lot of the content that they learned in school is also going to be tested on the exam, and people benefit when they just leave school because they're used to studying. It's kind of a muscle that they've been exercising for like 20 years at that point. And people who have been in practice a long time maybe have more experience, which is a big plus. But that's somewhat offset by the fact that they might have forgotten things from school, and they might have forgotten how to study. So the answer is there is no bad time to take the ARE. There's no good time because you're always busy, but there is no bad time to take the ARE. So those of you who are listening in and have not yet scheduled, I cannot stress enough to schedule. And actually, I want to stress something else. I think just about every 40 minutes of competence, I'm like, just take the test, sign up for the test, take the test. I just want to point out that the Amber book is a monthly subscription. So if I encourage you to stretch out this process, we make more money. But that's how strongly I feel about, well, first of all, those of you guys who know me know that I'm not driven by money on this. But that's how strongly I feel about this, that it is against my financial best interest to hurry you guys through this, but it is still in my best interest because my core mission is to get more of you licensed, and my super secret core mission is to make better buildings, or to help you make better buildings. All right. Now for next week, and you can take a screenshot of this, or take a phone photo of this, or you can make sure to get on our mailing list at firms@amber-book.com. And this is next week's question. So it says, how many foot candles would be measured 3 feet above the floor, directly below a fixture hung at a height 9 feet above the floor, given that it's a point source of light, and it's kind of emitting equally in all directions, and then it's 9,000 candle power, and you can ignore reflectances from room surfaces, dirt depreciation, etc. So that's your assignment for next time. This was a 26-minute competence, 26 minutes of competence instead of 40 minutes. But I'll go ahead and those of you guys who would like to go start studying, don't stick around, just go start studying. Those of you guys who would like to ask me some questions or like to listen while other people ask me questions, go ahead and stick around. So you have 1 or 2 minutes while I set everything up for the question and answer segment. All right, hopefully you can hear me, and hopefully you can unmute yourself if you want to ask a question, and you can go ahead and ask it.
Mike, I have a question.
Fire away.
Before I ask you the question, I'd like to tell you that I tried to schedule my exam, and I am in New York, but none of the exams are
None of the Prometric testing centers are open or available?
No. And then when I try to schedule an exam, it gives me the location, like, in Connecticut or in somewhere, Vermont, and those are the location that where I have to go and take the exam. So it means that none of the exam center is open in New York.
Oh, I'm sorry to hear that. That's so frustrating.
And then time's running out, and then now it's essential exam, but now people who like us are stuck in this situation.
When is the last time you tried that? Because the NCARB exam is now essential.
Yeah, no, but the exam centers are the option when I try to, and then I give the location, and then the location that they show,
right.
None of it.
Yeah, but have you tried it in the last 9 days?
Yeah,
okay.
Of course.
Okay. Oh, I'm so sorry to hear that. That breaks my heart.
Yeah. And then the exam, the question that I have, can you tell us a little bit about where to put the RTU on the roof, like the location, where to be?
Where to put a rooftop unit?
Yes.
Yeah. So that's a good question. So if you have a building, and this is our building in section. One option is to have some of this equipment on the roof, and it often is going to be the chiller itself is going to be on the roof. So the compression refrigeration loop, the machine that has the evaporator and the condenser, and that has the evaporator and the condenser and the expansion valve and so forth, the compressor, that can be in the basement, and that can be on another floor, or that could be on the roof. A lot of times architects will put it on the roof, and they like to put it on the roof because then they don't have to plan for it inside the building because it takes up a lot of room inside the building. And that's a pretty reasonable reason to put it on the roof, with a few caveats. One is, if you're putting it on the roof, that means you're cooling, you're taking water from a loop here. So there's a loop here inside with a fan on it, where the fan is blowing air from the building across our chilled water coil, and that chilled water coil is going to then go back up to the chiller. So it's kind of a loop, and the chiller is going to recool it. Well, you're taking water to cool it, and if it's summertime, which it is because the air conditioning's on probably, the roof could be easily 200 degrees because you're taking it and you're putting it on the hottest place. So it is often, almost always probably, less efficient to put the cooling equipment on the roof because you're trying to fight the heat of the roof itself and the heat of the air. It's 100 degrees outside instead of 70 degrees inside. So if you put that equipment on the roof, that's one reason not to put it on the roof. And the other reason not to put it on the roof is that this equipment vibrates a lot. So we generally don't want to put it on the roof. We generally don't want to put it on the roof mid-span. We want to put it at a column. So if that was the question you got, where you were being asked where to put it relative to a column, we want to put it over the column. Now, likewise, if we put it too near the edge, especially if it's a low building, especially if there's a hill up here, then I can kind of I could stand on my hill and I could look down. And these pieces of equipment, I don't know, as a profession, I am just so sick of architects just pretending like those things don't exist and acting like we had no control over it. So I would say don't put it somewhere it's visible, especially if it's a low building, it becomes a big deal. Now, if it's a 10-story building or something like that, it's probably only visible from taller buildings around, which may not be as big a deal. But if it's part of the kind of the community space, I don't think it wants to be visible. So I would keep it away from the edge. Although again, I'm not sure that NCARB, if they were asking you about that, if that's really what they're asking. And then finally, this is a really difficult question because from an efficiency point of view, you want a fan and you want short ducts because then you have less friction as you're moving. If the rooftop unit is moving air, if it's moving water too, you want short pipes. But if it's moving air, in other words, if this is a completely packaged unit where the chiller is there and the fan is there, so it's in that case, let me see if I can erase here. No, it's not letting me. But in that case, what we're doing is instead of bringing water down to here, we're bringing air. We're taking air from the building. We're bringing it up to the system and then bring it back to the building. If that's what we're doing, and I think often that is what we're doing in these rooftop units, if that's what we're doing, then you, at least ostensibly from the point of view of expensive running ducts are very expensive to run, and efficiency, because ducts make the fan, long duct runs make the fan work harder. You want the rooftop unit to be near the spaces it's serving. Now, I don't like to give that advice. That may be what NCARB is looking for, but I don't like to give that advice because if you have short duct runs, you also have a significant amount of noise. These things are noisy as hell. And so people will put them right over top of the classroom they're serving, and then you can just hear the fan all the time in the classroom. So I would put it over maybe the closet that's next to the hallway, that's next to the bathroom, that's next to the locker room, that's next to the storage room, that's next to the teacher's lounge, that's next to the classroom. Because all those other spaces also need cooling. So the ducts have to go to there anyway. So you want to put it, insofar as a duct run is going to serve multiple spaces, if possible, you want you want, at least 30, 40 feet, and if possible, like 100 feet of duct between the noisy mechanical equipment and the quiet classroom or band practice room or whatever kind of room you want that's going to be quiet. So kind of taking all those things into account, you don't want to see it. You don't want it to be mid-span because it'll cause vibration. You don't want the duct runs to be long in general, but you want them to be longest to the spaces that are most quiet. I think that's probably a good starting point. But frankly, in terms of those kind of questions, I'm not sure. In my experience, NCARB doesn't seem to be aware of the problem of the noise problem associated with short duct runs. It doesn't seem to show up in their test. In my experience, taking the test, and so I'm not. What's that?
What about wind direction?
Wind direction? I can't imagine that's an issue. I can't imagine a scenario where the wind direction would matter.
I see. Still got it. Thank you.
You're welcome. You're welcome. Who else? Who else? Anyone else? All right. Thank you, guys. Oh, someone has a question? Yeah, go ahead, fire.
I agree on there's no issue with wind direction because most of people now or developers now that I've noticed they tend to cover HVAC units above the roof with putting some barriers and enclosures around it. So it's not really a factor of where the wind blows as long as you have like some sort of 6 feet away from the barrier. That's where the they can suck air out efficiently. But I agree on what you have mentioned.
All right. All right. Well, thank you, everybody. And I will see you guys next week. Next week, we'll be talking about indoor light sources and directionality. All right. Take care.
Thank you. Thank you.
Bye.
Mike, can I ask you another question?
Sure.
You have
Sure.
I know that you are going to be, giving us classes at a session next week for light.
Mm-hmm.
But this one is, what is high grade energy to low grade use? Is that
Yeah. So you want, yes, I could talk about that right now. It's actually a pretty easy concept, especially given what we just talked about with fuel. High grade fuel. So you want to use high grade fuels with high sophisticated. I forgot what the words are that the people who study this use. But basically, here's the idea: you don't want to use. You can't use coal, for instance, to fuel your computer directly. Now, here where I am, 89% of the electricity that is produced where I am is actually burning coal, which is remarkable because in the Amber Book videos I talk about that 10 years ago it was more electricity created by coal than every other source put together, more than oil plus natural gas plus solar plus wind plus nuclear plus hydroelectric, all combined, did not equal coal. And then about 10 years later, coal was down to like 30%, which is remarkable because it's really expensive and time consuming to swap out your fuel source for electricity. Now, we're recording this during the COVID crisis, there was an article in the Times about 3 weeks ago that said for the first time ever, there's actually more solar and wind and renewables than coal, which is insane because 12 years ago, all the renewables combined were a rounding error. They were, 1% or 2%, depending on what state you lived in, maybe 3. And coal was bigger than everything else combined. And now coal is smaller, and coal has the highest footprint when it comes to particulates, and it has the highest footprint when it comes to carbon. So coal is kind of a wicked fuel source as far as I'm concerned. If you like clean air and you don't like atmosphere cancer, then I would say maybe limit the coal. Anyhow, so what's happening right now where I am is coal is going into boilers, actually very close to here, going into boilers, and then those boilers are making steam from water, and that steam is spinning a turbine, which is generating electricity. And so there are losses all the way along that line. So for every, it's actually, exactly what we were talking about. For every, in terms of efficiency, for every unit of energy of coal that goes into the system, once we've boiled it and spun the turbine and sent the electricity around the grid, we've lost about half of that, depending on the situation. So generally, it is best to use low-grade fuels for low-grade applications. A low-grade fuel is something like coal or wood, and a low-grade application is something like heating your building. So we can use wood to heat our building, but it's really complicated to use wood and then lose all that in the process, lose all that energy in the process, burning wood into electricity. So we would prefer ostensibly to use low-grade fuels like wood or coal for low-grade applications like heating. But something like air conditioning, that's something that we need electricity for. Or something like running my iPad is something that we need electricity for. We really can't use a low-grade fuel like wood or coal. We need a high-grade source like electricity, which requires often the burning. Often we have to have fission and uranium, or we have to have wind turbines offshore, or we have to have solar photovoltaic arrays, or we have to have big power plants that take natural gas or coal and turn them into electricity. So there's a lot more that goes into producing electricity, and there's also a lot more that goes into running a computer. So historically, what we've always said is we would like to pair high-grade high-grade energy sources with high-grade applications, and low-grade with low-grade, so that we can have a more efficient system overall. Now, honestly, some of the smart people are starting to change their tune on that. As we're producing more and more of our electricity with renewables, using electricity, which is a high-grade fuel, for something like heating, which is a low-grade application, is not seeming so crazy, because then we don't have to pollute the air and emit carbon in the air. So as we're starting to produce more of our electricity, and if you live in a state like anywhere, Washington, Oregon, California, almost none of your electricity is coming from fuels that are emitting carbon. So in a place like that, the environmentalists, the smarter ones, are saying, well, maybe that advice is not really as relevant anymore. Maybe now we need to start thinking about just having all electric everything. And so a lot of environmentalists like me, who have done projects recently, as I have, I'm starting to wonder. I was trying to always match low-grade fuels with low-grade applications, specifically heating. And higher, so that we're not using too much electricity for things like heating. Because where I live, almost everyone uses electricity to heat, and that's not a particularly efficient way to do things right now. But I'm starting to think that maybe that advice is not quite as powerful as it used to be, because in the future, I don't think it will forever be 89% coal where I live. It may be 100% electricity in 15 or 20 years. And that building and its equipment may be around for 30 more years after that. Hope that.
So like for domestic water heating, that would consider what?
That we would want a low-grade fuel for anything that just isn't. If it's just a matter of burning it with combustion and turning it directly to heat, we'd rather do that. Because, so if you're talking about, if the question is about a low-grade fuel for domestic hot water heating, then definitely we want a low-grade fuel, something like natural gas. Generally, what happens to make electricity, we have to burn it, then send it over wires, and then make it heat up the water. But we've lost a lot of heat in the process. So the idea is, why lose all that energy turning natural gas into electricity if that electricity is then going to heat your water? Why not use natural gas just to heat your water, and we'll lose less in the process? So anything that involves heating water or air is a low-grade application and can use natural gas or coal or fuel oil, gasoline, oil. Anything that is a high-grade application which is, you know, running a fan, running air conditioning, or running an elevator or running a computer, you have to use a high grade fuel like electricity.
Thank you. It clear, I have now clear conception about it. Thank you so much.
Good. Anybody else before we sign off?
Hi, Michael.
Hey.
Hi, I just wanted to ask if the Amber book is available as an e-version because at the moment courier services are suspended in Dubai,
Yeah.
so it'll be difficult to receive it.
The course itself comes with a PDF that you can print out or you can use on your screen. So yeah,
cool.
the course comes with an e-version. And actually, you know, at one point we kind of stopped sending the book years ago. People lost their damn minds. People were like, you have to keep, you know, you have to give us the book. So we made the book way better. We took it from, you know, 90 pages to 375. We added hundreds of illustrations. And then since then, you know, the more I've kind of learned about cognitive science, the more I've come to understand that the more senses you can engage while you're learning, the longer you have recall and the more ownership you have. So if you can use your eyes to watch the videos and the animations, and you can use your ears to listen to my voice, and then on top of that you can use a pencil to answer the question, that's probably better anyway. So I would suggest printing it out. I know that's a lot of paper, but I would suggest printing it out, but you certainly don't have to.
Okay, perfect. Thank you so much.
You're welcome. And the book, and those of you guys who have started the Amber book know this, the book is very much in support of the course, but there's lots in the course. Probably a little bit more than half the course is not in the book. The book is just there to kind of help you move along and give you a place to jot notes and that kind of thing.
Is it the right place to start? Because I kind of feel intimidated by the quantity of the material.
Yeah, I mean the course is definitely less intimidating than the book. The course is animated, and you know, it's not as much fun as you'd be having if you weren't studying, but it's more fun than you'd be having if you were studying anything else. So it's actually I would say if you find the phone call we just had fairly excessive, the phone call we just had, the Zoom call that we just had is more complex and more kind of in the weeds than almost all of the course, because the course animates it all, and because most of the stuff you need to study is actually not formulas. I'm going through these formulas because people always ask me about them and because they can be on the test, but actually the test is much less quantitative, much less numbers heavy than you think it will be if you haven't taken any of them yet. Out of 600 questions, maybe you'll have 6 or 7 or 10 that are kind of number based, and of those maybe only 2 or 3 are complex. The others are ones you could probably figure out if you can do the kind of things we just did. You could probably figure them out even without knowledge. So that the formulas are not that important. Now that said, the relationships are very important. So kind of understanding what happened, you know, what the concept of a full load hour is, and what the concept of a BTU per hour is versus a BTU, and what the concept of efficiency is. Those are very, very important to the exam, and will account for, you know, those kind of concepts that you have to know to be able to do the math. Probably account for 20 or 30 or 40% of the questions. So the beauty of the math is if you can do the math and you really own it like we do now with this problem, then you also can get those other questions as well.